Let me present another example. So this is another example B. Let me check. We have the following function. So let's say like this: integral, where you have c, and then you have here 1 over z divided by z minus a, or can be minus, can be plus. So dz, where c, put it like this, so a is different than 0, and c in this case will be the set of all z such that z is equal to equals to absolute value of a. Okay, so that's our integral. You can immediately recognize there are two singularities, so maybe write it down. Solution. So we have the function f of z, which is equal e1 over z divided by z minus a. So in this case we have just two singularities, namely z0 is equal to 0. It is clearly essential singularity. And another one, z1 is equal to a, and that's a pole. Simple. And let me look at the contour of integration. So we have here coordinate system. So the singularity, one singularity is here. This is 0. Another one we don't know what it is. Maybe a kind of a complex number a, which is here. But what I know is that the contour is is a circle of the double radius of this distance. So this distance is like a double. Sorry. Again, you have to add that distance. Oh. So this is my contour C. So we have here two singular points. So this one is z0, this one is z1. All of them are inside. So that tells you that yes, you can use the infinity, let's say the residue at infinity for this computation of this integral, and that's what we are going to do. So we put it like this c, and we put here like this e1 over z minus a dz will be equal, and we write down, so 2 pi r residue of the function e1 over z minus a at infinity. So to be more specific, you can convert it to the residue at 0, so it will be e z, and this one will be here 1 minus a z, and then this goes here, this will be z divided by z squared at 0. Here we have a small simplification, this cancels that one, and you are seeing immediately that since g of z is equal, let's write it down clearly, z, and this will be 1 minus a z times z. Z equals 0 is a simple pole. So the residue is easy to compute, and we obtained the residue of this g of z at 0. Okay, you can check it, plug it. This will be equal, the value of the is simply equal to the value of ez 1 minus az from z is equal to 0, which comes to 1, and then the answer is that this integral is equal to pi r, and we obtained. So to conclude the examples related to the Cauchy residue theorem, and to give you an idea about what kind of situation we can expect. Let me present you one more, let's say, example. Let me find it. So let me write it down. Compute the following integral. I forgot. Let's see. 3, I think. Compute the following integral. Let me see if I have this example. Okay, I remember. Okay, example number 3. It is compute the following integral. Integral, and this will be like this: integral c, this will be z, and this will be sine of z 1 minus cosine of z, yeah, dz, where c is equal to the set of all z such that z is equal to 5. So this is 5. Let's see. So let's see. And this integral has kind of an let's say like this. This integral is a good example for the practice of the computations of the residues, and you will see that there are always many possible ways you can go about these computations, but sometimes it is important to choose the one that is the most efficient. So let's see the singular points here. So put it like this: solution. So we see the singular points. Which are zeros of sine or zeros of 1. So maybe write it down: sine of z is equal to 0. That means z, you can write it down. We have here that z must be equal pi k, and that means k is equal 0 plus minus 1 plus minus 2, etc. Or 1 minus cosine of z is equal to 0, and that means that z must be equal to pi k, and k is again equal 0 plus minus 1 plus minus 2, etc. So you can see that we have many poles, but not all of them are important for these computations, and the set of, let's say, the singular points, the singular points of the function f of z, our function is z sine of z 1 minus cosine of z, are not bounded. So in this case we cannot use the residue at infinity, so we need to compute this directly. So we need to find out which are the residues that belong to the which are the singular points which belong to the contour of integration. So let's see how many residues do I need to compute. So let me start. So I have here like this 5. So let me see where are my singular points. So this is 1 is equal to 0. Another one is pi. Pi is about minus pi is here. So then it is 2 pi is here. And minus 2 pi is here. But the contour of integration is around 5. So this is somewhere here. This is c, and that number is 5. So you can easily recognize there are only 3 points, singular points inside. there are only 3 singular points inside. So let me see. So let me see. You can notice. So first remark. So remark, or maybe notice that for z0, which is equal plus minus pi, those are these two, z0 is a simple pole. Yeah, you can see it. Cosine will be different than 0. So let's justify. This is z. This is 1 minus cosine of z, and this one is sine of z. So you can see that function. If you put here z is equal plus minus pi, that value is different than 0. Different than 0. But that one gives you 0. But derivative cosine of z at that point is equal to minus 1, is definitely different than, so it's different than 0, so this is a simple pole. If this is a simple pole, I can write it down, then residue of my function f of z at the point plus minus pi will be equal, so let me substitute, so this will be plus minus pi, and here I'm getting 1, 1, so 1 minus, so this is minus cosine of my, so this is minus 2, and everything, not very nice. Maybe write it down like this again, so this would be my plus minus pi divided by minus 1, and here we have cosine, so it again will be equal minus 1, and you look at this and say like this, minus 1, so you have plus minus pi over 2. Yeah, so we have it. That's the easy part, and now we need to compute the residue of the function f of z at 0, and here we have a little surprise. This is kind of an ugly pole. So here, let me write it down. Our function f of z is equal to z divided by sine of z, 1 minus cosine of z. So we have here that 0 is the order of 0 for sine is, sorry, order of 0. So we know that this is 1, and here you will see this is 2. So one of them is here, one of them is cancelling here. This is order of 0, at the top is 1. So we can recognize that order of pole z0 is equal to 0 is 2. And then we have the choice. Maybe just do the choice number 1. So apply the formula, namely residue at the f of z at 0, it will be equal, so we can write it on 1 over 1 factorial, limit at z goes to z0, and then I have here f of z times z square, evaluate the derivative of it, of course, derivative of it, and then f of z times z squared at the point z equals 0. So let me rewrite it down. So this will be limit. What is z0? Okay, this is 0 again. Z goes to 0. And then you have dz. And then we are getting here, this is z cubed divided by sine of z, 1 minus cosine of z, and okay, I leave it to you. I already see that this limit is ugly and may not be very easy to compute. I don't like it. I don't want to do it. So the rule is, let's say, if you can think about something better than that, then of course it will be much more convenient for you to apply something that gives you the result faster than just fighting with the long and complicated limits. So by simple laziness, we abandon this way of computations. And we know that there's another way trying to figure it out, what is actually the Lorentz series let's say a-1 coefficient. So we will try to find coefficient in Lorentz series. So let's start doing it. So here we have f of z, it will be equal z, and then we have the product. Here we have the product. So what is our product? So the product is, okay, first one is sine of z, another is 1 minus cosine of z. So let me write it down. So this is z, and what do I have here? Here I have power series expansion. So this will be z minus z cubed 3 factorial plus z5 5 factorial minus. And then what do I have here? I have here 1 minus 1, so this is 1, and then we have minus 1, and then we have plus z squared divided by 2 factorial minus z4 by 4 factorial plus, like that. Very nice. You can continue. So you can see, you can pull out the z out. So this out goes out, this z goes out, and this z square goes out together with 2. So what do I get here? I'm getting 3. So here we have z, then this 2, number 2 that is here, you see, I also put it here. So let me put it like this, 2, this number 2, and then I have here z, and this will be z cubed, then I have here 1, and then I have here what do I have here? I have here, okay, I have here minus z cubed divided by 3 factorial plus z5 divided by, sorry. No. 1 minus z squared 3 factorial plus z4 5 factorial minus extended, and here we have here 1 again, and this will be minus, and this will be z squared, but now it's times 2 divided by 4 factorial plus z4, sorry, this is 2 factorial, and this will be z4 times 2. So maybe I should explain where this 2 comes. So remember, we pulled out this 2, so this is this 2 here. You have to remember, I have to add it here. So that's how it is. So this will be 2 factorial, this will be plus z4, so we are here, you have to multiply again by this 2, and then you have here 4 factorial here, and blah 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 minus, etc. So you have here like this. So of course there is a simplification. You are immediately getting this 2z squared. Those two are analytic functions, so this is analytic function. And we know how to multiply the Taylor series expansion. We just need few terms of this expansion. So let me say that's a two analytic function. I need few terms of this expansion. So what do I get here? I'm getting here first that this one is 1, and then I have here z squared. So let me write it down. Actually, you can notice immediately that this one will be something that looks like that. I don't really need to find exact value that one. Just need to notice that all the powers here are positive. But we will do it. We will just do it like it is. So I'm getting minus, and then you have here z squared. Sorry, z squared, and what do I have here? 1 divided by 3 factorial, and then it is again 1. So this is 1, 2 by 2 is 1, so this will be like a plus 1. And then I have plus, and this will be z4. And what is z4? Z4, this will be like this, so this will be again, what do I get here? I'm getting 1 over 5 factorial plus 2 over 4 factorial, and then have plus again 1 over 3 factorial, which is this 2 product of this 2, and then minus another one, and so on. And then you do the usual thing, usual step, use it as a q. So you can put it like this and change it to minus. Oh, sorry. So this will be your q. So of course it has to be changed to minus, changed to plus. Maybe I should make it more clear. Red one. So this might change to minus, this one change to, and this will be your q. So this is 1 divided 1 minus q. You are getting here, this one is equal, n is equal to 0 to infinity qn, and you are obtaining that this is equal to z squared, and we can write it down 1 plus, and then you have here z squared 1 3 factorial plus 1 plus z4 1 5 factorial plus 2 4 factorial plus 1 3 factorial plus, and then you have another one, the same square, and then you are looking for the coefficient. Which one? A minus 1 over z. Here are even coefficients in this whole expression, only even. This is even now. You cannot get a minus 1. So you cannot. A minus 1 is 0, so you are getting a minus 1 is definitely 0. You cannot have the coefficient, non-zero coefficient, standing by the power, negative power of z, negative z to the minus 1 power. Z to the minus 1 power. Square is 0, that's the first power. So, okay, so in such a case we finish the computation, because now we can write the answer. Answer will be this one, so let's write it down. Integral c, and this will be z dz divided by sine of z 1 minus cosine of z is equal, so we have here 2 pi I. That's usual, and then you have here residue of f of z at 0, and we computed it. This is 0 plus, and this was a residue of the function f of z at the point minus pi plus residue of f of z at the point plus pi, close it. So what did we get here? We get here this was equal minus pi over 2, and this was equal pi over 2. Let me check it. Let me check it because we have to go back. Oh yeah, this was here. Minus pi over 2, so it is correct. So I'm getting here, this is 0, this is also 0. And we finished. So thank you, and the next week we finish the class with the applications of the residue theory to compute, actually to do some computations, mostly like integrals, improper integrals or trigonometric integrals. So thank you for now, and we will meet again.